Okay, now the record is on. So let us go back to our design. Okay, now generally you have some idea now what section that you may be using. So let's say you're going to make some choices now. Okay, and our target is 333, right? So the first section that is available here now, you use this section. See, you may begin from here. See that? That's 366. So I'm just going to put it there. H 250 by 125 by 29.6 kilogram per meter. And then the ZX here is going to be here, 366. Okay. It's too close. Let me try to move this a little bit. It's going to cause some. Okay, not too bad. So it's 366. And now, next one, you see, let's compare it, okay, for the sake of comparison. Now I'm just going to put the column section in there as well. You can see next one is 175 by 175, and the ZX is 369. Oops, I've got to wait. 40.2. You see, this is where we judge the economy of our design. See, it's pretty heavy now. The next section is going to be 300 by 150. See, it makes kind of sense, a lot of sense. You have a 50 millimeter more depth with the weight only increase slightly. So this is 300 by 150 by 32. So compare this. See, it weighs more than this slight bit, but it weighs a lot less than 175 by 175. Okay, here is 475 for the see the plastic section models. Okay, let's throw in two more for our consideration. It's 200 by 200 and 300 by 150. Another one. Okay. That's 49.9, heavier than 175 then. And yeah, now you have more plastic section modulus with a lot more weight. Now you see, compare this. It's like 50% increase in weight. And the next one is the bigger 300 by 150 by 36.7. This one has 542 plastic section modulus. So it's pretty interesting. Okay. Now I have to say that say this is column section, and you see how ineffective they are in terms of the weight versus what you're going to have in terms of flexural capacity. So I'm not going to use them. Okay? So now it's discrete. And let's again assume that we're going to have compact section. And say I can go ahead and calculate this. Oops. MP over factor of safety, because we're going to assume MP, right? Assume compact as usual. So MP here, I don't know if I have enough space to write, but let's say that's going to be 2500. And then multiply by 366 divided by 5/3. And we have a moment in kilogram meter. So let's divide by 100. Okay. I seem to be out of space a little bit, so I'm just going to move the entire thing again. This last sorting is very convenient, isn't it? Okay, so now it's that is 490 kilogram meter. See, it already exceeds 5,000, so we are fine. Okay, for this section, we increase the weight only like 2 kilograms per meter. So look what we're gonna have now. So now we have 2,500 multiplied by 475. Divide by factor of safety and then 100 to change the unit. So now I have 475. That is 7,000. Okay, let's use a 3 significant figure. That's fine. So you see, wow, I have a lot more by increasing the weight just a tiny bit. So I say now I am very interested in this one. Okay, but just let's go on for another one left. Now this guy MP over factor of safety, that's going to be 2,500 multiplied by 542 divided by factor of safety and 100. So this I got 542. So that's 8,130 kilogram meter. So I am very interested in this one as well. But notice that all three pass the strength criteria. Okay. So now, what are you going to do? Now, let me point out another thing for you. Let us go back to the same table. Now we are looking at 300 by 150. Here. Okay. So try to improve. All right. So we are here. Both of them seem to be good enough. But one thing that you also need to know that just look at this. This one, the heavier one, the 36 by 0.7 as a kilogram per meter, it has the depth equal to the nominal depth and the width equal to the nominal width. And chances are that in the market, you are more likely to find this one available easier than this one, because generally the manufacturers would just manufacture the ones with the actual size equal to the nominal size. So this is a good choice. Okay. And I say, I'm going to go with this one. In fact, if I'm a little bit stingy, I go with the 32. Okay. But just to say that when we look at the design, from 29 kilogram per meter to 36, that's not a lot. Okay, still much lighter than the column section. Now, keep in mind that, let's say, you are a person who follows just the number, and say, why not? When I reach the number, I'm just going to use this one. It's 175 by 175. Who's going to do anything to me? Nobody is going to do anything to you, because theoretically you are correct. But only engineers will know that, well, this is not a good design. So you can say that, nobody is going to be able to say this is good engineering work or not, because what we do is pretty advanced stuff. So, if your heart is broken, well, you're just going to have to live with it. The fact that, you know, nobody can appreciate how good you are. Okay. Unlike, you know, oh, hey man, you danced so well last night. You're dancing, just anybody can see that. But that's not also true, because you know, the advanced dancing will have to be seen by professional eyes as well to be appreciated. And likewise, here you can choose any section and you'll be fine. Nothing is wrong. But say you are not designing something very economical. That's all we can say. Okay. So now we are going to proceed, because we are done with the prelim design. So we're going to try H300 by 150 by 36.7 kilogram per meter SS 400. Okay. Now the first one, local buckling. Okay, sorry, I didn't write the properties of the section around here. The flange local buckling, the BF over 2 TF is equal to, you can just come back here and look at this table there, 8.33 and 39.4, right? 8.33, you know the number. This is surely it's going to be less than, what's the 0.38, right? Square root E over Fy, which is roughly 10.8, am I right? Yeah, right, 10.8. So we now have the compact flange. And now with local buckling, H over TW, that's 39.1. Can you recall? 39.4 there, you see? 39.4. Surely this will be less than huge limit of 3.76 square root E over Fy, which is 107. So it's compact as well. So you can now conclude that it's a compact section. Okay. So we go on to step number 2. Okay. For the nominal moment. M nominal is going to be equal to, because we have the compact section, so it's going to be Fy multiplied by Zx. Correct? That is 2500. Our Zx is 542 divided by 100 to get the kilogram meter. So it's wow, a lot. Kilogram meter. Now, what do we have here? We have MA, right? And so let's go. M nominal over factor of safety, that's this divided by 543, right? Remember that I use 3 significant figures. This is not the exact number. If you punch a calculator, and this is equal to 8130, which is greater than the moment that we have from the load, which is equal to 5,000, right? So we get the big OK. And let's take a look at the weight. Now we have 36.7 versus the assumed number of 100. You may want to go back, but you know you get the number less than 5,000 here, right? So it doesn't affect anything. So you say, okay, it's fine because the weight of the beam that we actually use is way less than the assumed number. So if you go back and calculate the actual moment, which you may want to do, but you don't have to, you're gonna get the real number less than 5,000. Or maybe you say, hey, you're not doing things right. This is not 5,000. Yeah, fine. We can say that the MA is in orange, 1,500 plus 36.7 and 5 squared over 2. Oh, 8 over 8, sorry. Okay, so that's only 4,800 kilogram meter, which is, okay nonetheless. Now, you will know why. Now it's two things, right? We check two issues under bending moment, the local buckling, and then the flexural capacity. We are going to move on to check the shear capacity next. I thought I have this, but I don't. But before we move on to shear, so let's do this first. Okay. Number 3. Oops. Serviceability. Service and ability. Okay, now you see why, remember it's service load. Oops. And deflection is equal to 5 over 384. Remember that? And WL power 4 over EI. So now, from that, now we are reduced to 3, but let me show you something. So I'm just gonna investigate these 3, okay? Now with this H 250 by 125 by 29.6 kilogram per meter. I suspect that it's going to start off in a bad position again. Okay. Yeah. So at the moment of inertia here, you can go back and take it from here. 200 and 125, 29.6, that's our inertia, right? 4,050. Okay, oh, it doesn't look like 5 at all. And for this H 300 by 150 by 32, the inertia is right here. That's I coming down here. You see 11,000 now. Oops, sorry, that's the wrong one. 6,000. That's more like it. 6320 and 67210. And 7210. That's for each 300 by 150 by 36.7. Okay, so now I am going to calculate this, and it's going to be 5 over 384. This is going to be 1,500 plus the weight. Okay. All right, and to handle, here we go again, outer space. And to change the unit, because this W is kilogram per meter, so I'll multiply it with 5 and then 500 cube. That's how I do it. And then E is roughly 2 million. And then divided by I of each member. Now, after doing this, I got the deflection here equal to 1.51 centimeters. This is 0.967, and this is 0.85. So let's say I consider L over 360, the total load. L over 360, L is 500 centimeters, right? So that gives you the limitation of 1.39 centimeter as your limit if you are going to use this as your deflection criteria. So that means, you see, that one is beyond. By increasing the weight a tiny bit from 29.6 to 32, now your deflection is reduced dramatically. So that is the one of the reasons behind the fact that I choose to go with either one of these two, and to make sure that I can procure it very easily in the market, I'll go for the more common section. Doesn't hurt much to add more 4 kilogram per meter more. Inertia also increased more as well. So that will be my design, but we are not done yet. We are going to have to check the shear as well. Okay. Okay. So for shear now, say local buckling, and the H over TW, you already pick it up from somewhere, right? It is right here, 39.4. Just a second. Okay, so now we are going to compare this. Let's say if you don't want to be bothered, you can use 2.45 square root E over Fy. This is roughly 70 something, if I'm not mistaken, but I don't remember for sure. Yeah, it's about 70. Now, if you are curious, 2.24 square root E over Fy is about 64. So see, this is less than these two values. So you see, your CV is going to be equal to 1. So you're free to use either factor of safety equal to 503 or 1.5. Okay. So let's say now your nominal moment is going to be equal to 0.6 Fy. The total depth now, because we use the one with the size equal to the nominal size, so it's pretty easy, 30, but you're gonna have to pick up the TW. Here, TW, here, 6.5 millimeters. See, it's pretty thin. So it's 0.65 here, and divide this by 1,000 to get the tons unit. So that's about 29.2 tons. So you're free to actually use any factors. Now, let's say for factor of safety equal to 1.5, we're going to get this equal to nominal divided by factor of safety, it's 19.5 tons. For this, if you are conservative, This is going to be about 17.6 tons. Now you've come this far, you realize one thing. Hey, we haven't calculated the shear force, right? So yeah, it's a VA is equal to WL over 2, right? Now you may want to use actual load, that's fine. It's a 1500 plus 36.7 multiplied by 5 over 2. That's in kilogram. So let's divide it by 1,000. That's only 3.84 tons. So you can see either one that you want to use. You can say now that your V nominal over factor of safety is greater than VA. So it's a big okay. So now we have checked everything and we can conclude that we are going to use H300 by 150 by 36.7 kilogram per meter SS 400. So that's the end of your design. Any question? Any question, please? So now you see, if you focus on the level 3, you know, go back to outcome rubric, and I say that identify the relevant failure mode here. See that? The relevant failure mode here would be is 1, okay, 2, and then oops, 3, and then 4. If you've come this far without doing any calculation correct at all, this is level 3, which count for 10 more %. See, if you can do all this, if you can identify everything, the ASD, the use of factor of safety, the correct FY, and then every failure mode accounted for, you now add the threshold of an F. It's 40%. Anything you can do beyond the this, you know, the calculation will be distributed over the 50%. Okay. So I think that's it for today. I can go on some more, but you know, I don't think there's any need for that, because next we're gonna take a look at not this one. We're gonna take a look at some other relevant failure modes that involve the beam. For example, your beam can fail when it has the point load acting on it like this. This is going to lead you to another design of the base plate of the column as well. I guess we can do it next week. Okay. So any question, please? That's it.
Actually, for CV is equal to 1, that means we cannot see that, right? In this
you
case,
cannot what?
Yeah, cannot see number 1 multiply with VN, right? But actually, it will be.
Yeah, you know, if you want to be extremely correct, you should say multiply by 1 here. But you know, it's not going to change anything, is it?
Yeah, okay. Just only observe for the equation.
Yeah, good observation. Good. So more questions, please. Okay. Any question, please, guys? Hello. Hey. So I think I'm gonna stop the record then. If nobody is gonna ask me a question, because you know, every time I stop it, it seems interesting questions pop up, and it's off the record. But if you continue to be quiet, say for 1 minute more, I'm just gonna stop the record. Okay. Any more questions, perhaps? Hello.
Excuse me.
Yeah.
For 0.5, where it come from? 0.5.
Which one?
Sorry, 0.65 for
0.
VN. 30 times 0.65. This is
Oh,
how
that's
we are available.
T web.
T-web. Okay.
Let me write it down. That's D. That's TW. Maybe too quickly. So let's go back. See? That's TW. 0.65 because it's 6.5 millimeters, and that's the actual depth. Okay, so basically it's just these two.
Okay, thank you.
Cheers. Any more? Oh, I'm off the camera. Any more questions? Hello? Anyone?
I guess today is very clear and anyone will not have
It
any
is.
questions.
You know, I think up until this point, compression member, flexural members, they are easy. But you guys may struggle a little bit when you try to handle the load on your actual building in the project. That seems to be the case. Who says steel design is difficult? It's pretty easy. Yes, it is. So you shouldn't be surprised if it's easy, because it is. I don't do difficult stuff, man. Okay. So let us stop the record. There's more people are leaving.